Good afternoon, everyone. Last time we talked about non-uniform bars. Anyone remember? So we say if there is a bar and the actual load, but it was a non-uniform, then the total elongation will be equal to the elongation of all the segments add together. Right? So you may have a non-uniform bar that's non-uniform in terms of length, in terms of area. So there'll be area, material, or the length can all be different, or can be the load, the N, all be different. Then we calculate each individually and get the total by add them together. And then at the end of class, we had this example. That is, when you have a load applying to a bar at mounting between two walls, right? So you have a load here. Let's say, make it easier, we have this right at the middle. Right? So you're going to have RA and RB here. So this will be RA, and then this will be RB. So we said you can write only one independent equation of equilibrium, and that is the N1, that's here. So this part you have N1, and then this part you have N2. So you have N1, right, and then plus N2, and then plus P equals 0. Actually, we have this free body diagram, so you can draw here. So this part is N1, and then this will be N2, right? So the load P is right in the middle. So we're drawing this middle segment, right? Okay, so since there are only one independent equation but two unknowns, so we cannot solve it. So we call this indeterminate. All right. Okay, so in summary, what's an indeterminate problem? It's when you have more unknowns, more reactions, then you can solve, just use the equation of equilibrium alone. Okay, so let's look at this example. See how can we solve this, right? So we draw the free body diagram and also equation. We know it's not enough. So what can we do to solve this problem? Okay, so we know you can, the equation of equilibrium, you can also write many other forms, but they're all not independent. So they basically can derive from this equation. Okay. So now we need to look at this. What happened in this problem, this example here. So when you actually applying load at point P here, let's say you're applying load here. Okay. Now imagine you're applying the load. So this bar A, C, and BC, they are not rigid, right? So that's different from statics. Okay. So let's say if this point C is going to move to here, then you're going to have a distance, this small distance, delta, right? So if this point moves, actually when you apply load, it will move because it's elastic object, it's not rigid. So when they move, and then the two parts will deform, right? So the AC part will get stretched, and then maybe the CB part will get compressed, most likely, right? You have to do that, otherwise this point C won't going to move, right? Or the part's going to put apart, going to be pulled apart, right? Break apart at point C. Okay, so if we look at this bars, let's say the bar AB, AC, okay, and also bar CB, right? So both of them are going to deform, and we know from previous equation that, okay, so the delta, the bar AC, right, or that is the first bar, so we can say delta 1, and that will be the force in this one, right, and then times the length L1 there, and then the material and the cross-section area. Okay. Also then we have delta, the CB, right, and that we call delta 2, and that will be N2, L2, and then E2, A2, right? And we know E2, A2 equal E1, A1. All right. So this one give us the relation how these two bars are deforming or elongating. However, since we don't know N1, N2, so we cannot find it, delta 1, delta 2, right? So how can we find it? So we have to somehow look at this deformation, see how the deformation pattern is forming between these two bars, right? So for example, for these two bars, we say if point C, okay, going to move a distance delta, then AC, right, must elongate, right, delta. Well, the CB, right, at the same time must shrink, right, delta. So, in other words, we can actually find out the relation between the deformation of those two bars or two segments. Okay, so what's the relation? We must have delta 1 equals to negative delta 2. Right? In other words, one is elongating, another one must shrink. Right? Or you can write it as, so the delta 1 will equal to this delta, but delta 2 then must equal to the negative delta. That's another way of writing. Right? So mathematically, these two are different, but physically, this means the same thing. Okay. All right. Or, in other words, we can look at these two bars because they are between these two fixed wall, right? So if bar 1 elongate delta 1, bar 2 elongate delta 2, then they both together, they will elongate, right? So they will elongate the total. The delta total of this bar 1 and the 2 will equal to delta 1 plus delta 2, right? And that, when you put together, right, because you're between two rigid walls, so how much you can elongate? It must be 0, right? So there's this three way of writing as equation, as a relation, but they all mean the same thing, right? Okay. So this kind of equation, we call it compatibility equation. And I just use the compatibility, so I say comp for short. So the compatibility equation is basically a relation between all these deformations. And this equation, that's an additional equation, independent of the equilibrium, right? So now we have two equations, different equations. You can actually solve two unknowns, right? Because this equation, that's equation 1, and then we have this relation that we say equation 2, and then the third set equation, that's compatibility. So if we combine these three set equations, then we can solve for it, right? Of course, there are multiple ways to solve this group of equations, but they all basically depend on or based on the Gauss elimination. So you can cancel out, eliminate some variable, and then solve for it. Okay. So for example, we can link everything to delta or to n. Right? So let's say if we link everything to n, right? So have n1, n2. Then we can say, okay, so delta 1, as we see from the deformation equation, right? So here, okay, so we have this delta 1, delta 2. Okay, so you can take this into equation 2 into this equation, for example, or into this equation. They're the same. So then you get, okay, that's what you'll get N1, L1, and then EA, and then plus N2, L2, EA. Right? So that's delta 1 plus delta 2, and that should be 0. Okay. So combine 2 and 3, you can get this equation. Okay. Now, use a simple case. Let's say assume L1 equals L2 equals half L. Right? Then this immediately gives us that N1 plus N2 equals 0. Okay, that means N2 is a negative N1. All right. Now take this back to equation 1. We'll get what? You'll get basically 2N1, right, and equals to P, and therefore N1 will be half P, then N2 will be negative half P. Okay, what does negative mean? That means the direction will be different. That means N2 here is actually going this way, so that's the N2, right? Actually, that makes sense, because if you have a load P applied in the middle, then the two person holding the 2N will feel, right, the pushing, and so they will apply a reaction, both pushing against the P, right? And they happen here that both bars are two sides are equally strong, equally stiff, so you're going to get equal load here. So if the N1, N2, so this one here, so if this N1, if the N1, N2 are not equal, right? Actually what I mean is if L1 not equal to L2, or E1 not equal to E2, or A1 not equal to A2, then that's a general case. So you'll have N1 and N2. They will not be equal. Right? Okay. So this kind of illustrate the process how we solving for indeterminate problem here. Okay. So in summary, okay. So one is okay. What's an indeterminate problem? You have more unknowns, and then you can solve based on equation of equilibrium. Right? And secondly, how to solve it? It's actually a 3-step process. So you draw the free body diagram here, right? And that's the free body diagram. Okay. And then you write the equation of equilibrium, and then you find out how the deformation are related. So then you the deformation equation, and then so here is actually the deformation equations, right? And then you actually find out the compatibility equation, right? So this is the compatibility part, right? Okay, so we can actually put this into acronym help us to remember. So basically the FED.com. Okay, so the F for free body diagram, E for equation of equilibrium, and D for deformation, and then compatibility, that's the compound. Okay. All right. So any question here? All right. Okay. If not, we'll move on to talk about next example. That's when I solve this equation, I'll get this one is positive, one is negative. Because here, I don't know. I assume everything is positive, right? So that's why I'll point in this direction. But when I solve that equation, you'll give me N2 is a negative value. That's mathematically. Physically, it makes sense because someone is pushing here, right? Have you ever had a chance you're holding a bar? Right? Imagine you're holding a bar. Now someone is pushing this bar to that side. So what are you two going to do? You're all going to push this way, right? So depending on how strong this two person is, they may share, or how hard this part is, they may share a different load. But in this ideal situation, they share equal load because these two material, they are the same length, same modulus, therefore same stiffness. It's like you're holding two springs. These two springs, they're the same, and then each one share equal load. Right? So these are like the spring, basically like the spring constant, EA over L. That's a spring constant. All right? That's a good question. Any other question or comment? Yeah.
Now that you explained it, it seems intuitive, but does it make a difference at all that in the example we have the force almost in the center, if we were to shift the force in another direction?
Okay. The question is, what if you shift this force, not in the middle, maybe somewhere here, 1/3 or 1/4 of the distance, or maybe 1/3 on this part? Will the solution be different? The answer is yes. The reason is here. Look at this equation. If your L1 and L2 is not equal, then the solution will be different. Right? So, physical common sense. Okay, if I pull in close to this side, right, you can do this experiment afterward. 3 of you as a group. Okay, one person pulling here, 1/3 of distance from this side. Who will hold more weight? Who will have to generate more resistance? The one closer. Because let's say you want to move 1 millimeter out here, right? You stretch this short distance versus you compress this long distance, right? A shorter bar, it will be hard to stretch 1 millimeter compared to a long bar. Is that correct? Right? Remember that equation. We have delta. Let me start writing here. Okay, so we have equation delta equals to NLEA, right? So if you push it, okay. So while this button, when press on, it will switch over to the other direction. It's this one. Okay, 1 second. All right, works. Okay, so based on this equation, right? If your L is shorter, right? You want same delta. Then you have to have a bigger N. So therefore, if you are moving this force here, then the guy on the left is going to hold more force. All right. Okay. Any other questions? All right. So here, this is one example of indeterminate problem. Okay. So from this example, I want to come up two main points. One, what is an indeterminate problem? When you have more reactions, more unknowns, then you can solve based on equation of equilibrium, right? For this problem, I can only write the one equation, two unknowns, so it's indeterminate. There may be other problem, I can write two equations, but I have three unknowns. Then it's indeterminate. Okay, that's point number one. The second point is, how do you solve an indeterminate problem? Okay, so here's my short summary here. I call it Fed. What happened to here? Okay. And let me see if I can change it. I don't know what happened here. Why it happened again? All right, give me 1 second. Eraser, and erase it. Okay, now it works. Okay, so I call it fed.com. So that's my trick for this class. Okay, you're going to use it again in this class. That's why I mentioned in the introduction, right? You all know what's fed.com. Okay, what's fed.com? Okay, look at this process, how we solve this problem. You draw the free body diagram. So that's the F part. You write the equation of equilibrium. That's the E part. And then you write out the deformation equation. So that's the D part. And then compatibility. So that's the com part. So basically, whenever you see an indeterminate problem, here is how to solve it. F, E, D, then com. You lay out all the equations, then next just mathematically you solve it. All right? So that mathematical part, I believe you all take the calculus, you know how to solve the equation. So I'll leave that part to you. All right? But this Fed.com part, we're going to practice again and again in class and the homework and the quizzes and the exam, of course. All right? Okay. So that's the acronym for how to solve indeterminate problem. All right? Okay, this is unique. If you talk to anybody else, they may not know what's Fed.com. So when you talk to another school or other professors, don't use this one. They don't know what it is about. I'm just making it this way so everyone can remember it. All right? Or you can explain to them. That's fine. Okay, what does FED stand for? Anyone can explain? Free body diagram, equation of equilibrium, deformation equations. In this case, elongation. Then compatibility. All right? Okay, now for the first one, here is another example. Okay, this is a determinate system or indeterminate system. What we have here is a rigid bar. Okay, that's the AB. A rigid, or we call beam, rigid beam. And then it's supported by a bar, a cable, CD here. So what I'm trying to apply is a load P here. So my question is this determinate or indeterminate? How do you find that out? Label, draw the free body diagram, right? Label all the unknowns. Say how many unknowns do you have? And then see if you can solve it by equation of equilibrium alone. Okay, so let's draw the free body diagram. Okay, this is the load, P here. Where's the action reaction? I can select the whole system, right? Okay, so what's the reactions? At point C, what do you have? This is going to pull it up, right? Oh, so this one, I think I need I'll label it here. Maybe use hold on, let me use a different color. Okay, let's use a red color here. So you're going to have a reaction force here, right? We can give a name, call it what? How about call it N? That's the internal force in this bar CD, right? Okay, what about point A? What kind of support you get? What kind of reaction you get at point A? This point is a joint connection, right? It's like this. So you can move around, right? But you cannot go away. It's like this point. So we call that a pin support. Okay, so we'll talk about pin support later in beam chapter. But here you need to know what's a pin support. So put a note in your notebook. Pin support means you can free to rotate. So there's no movement. But you cannot move away. So there will be reaction forces. So you're going to have here, we'll have a Ry. Right? What about Rx? Will you have Rx? In general, you may. But in this case, there's no force, load in the x direction. So all the force in x direction will automatically 0. So you have only one Ry there. Right? And the moment here will be 0 because the pin support. Okay, now how many unknowns do you have in this situation? You have a Ry, you have an N. So you have 2 unknowns. Right? Okay, 2 unknowns. How many equations do we have? 1? Or maybe 2? Okay, let's write it, say what, since this is the first example. Okay, so what you can write is sigma Fy equals 0, right? For this system, should the sigma Fy be 0? Yes. Okay. So what do you have? Sigma Fy equals 0. So you have Ry positive plus N. Then minus P equals 0. Right? Okay. Now, is this determinate or indeterminate? Or do you have more equations, independent equations? You can write, in general, okay, when you have a 2D problem, how many equations you can write? 3, right? So you should have sigma Fx equals 0. Right? In this case, here everything is 0, 0, automatically satisfied. What else? you can have a moment equation, sigma m, to a point. Which point you want to pick? A. Okay, so to point A equals 0. Now, what's this equation? Translate. So n times the distance of AD, right? So I just write AD distance. That's pulling upward, counterclockwise. Then what else? You're going to have a minus P times AB equals 0. All right? So, can you find out the n from this equation? Yes, you know the dimensions, right? You give your structure so you can measure the dimensions. So therefore, from this one, you can find out n. Now, can you take it back to the previous equation? Find out Ry. Yes. So you can find out Ry and n. The two unknowns, you can find out with two equations. So 2 match 2. Therefore, this one is determinate. Okay, so this is determinate. Put the mark there. Once you see this, it's determinate. So we don't need to solve it as indeterminate part. We don't need the compatibility part. Okay.
So is n the reaction at point C or just force?
Okay. The question is n the reaction at point C or is n the internal force in CD segment? They're the same. Right? Imagine you don't want to draw that way. You can make a cut here. Then you're going to have n here. That's the internal force, n, right? But the equation basically is the same. So basically, when you have a bar that under simple bar, when I stretch it here, right? I'm stretching 5 Newton. Then in this bar, the internal force will be 5 Newton. What's the reaction here? 5 Newton, right? They're all the same. All right? Okay, any other questions about this problem? What about point D? Okay, what is about? Yes, there will be reaction force. But to me, I'm drawing this whole system, so it doesn't show up. If I don't want to draw this way, so another way I can draw a free body diagram. Let me just draw it here. So I can select just this bar AB. I select this AB as my free body diagram. So I'll just draw it here. This is the AB, AB. This, right? This is my free body I select. Then I'll draw, okay, reaction here, Ry. And then you're going to have a reaction N from here. And then you're going to have the load P here. That's the free body diagram. Right? But does this change anything? No, it's the same. So there's no unique way of drawing free body diagram. Right? But you fundamentally, your equations, they're all should be the same. All right? That's a good point. I'll bring it up. Any other questions? No? Okay, now let's move on to see our next example. So I put the picture here so it looks a little bit nicer than my hand drawing. Oh. Okay, so here is your next problem. We have a similar situation, but now I feel if you just put one bar there, I don't feel it's strong enough. I want to build a strong structure system. Right? So I put another cable beside it. So in addition to CD, I have a EF. Okay, we can make it easier. Say EF is the same length, so it's actually here. So this is the EF. Same length, same material. We make everything the same. I just put 2 cables there. Right? This structure looks like a little bit more stable, right? Seems you can support more load. That's why I add a cable there. Okay, now the question is, first, is this an indeterminate or determinate system? Second, how to solve it? Okay, first question, is it determinate or indeterminate? How many unknowns do you have? Let's draw a free body diagram, right? So we can make a select, which one you want to select as your free body? Okay, my question, hold on. My question is, which part you want to select as the free body? The whole thing or just the beam? Just the beam. Okay, so we'll do just the beam. All right, so if I select just the beam, so you will be here. You go. So just the beam, right? So this is the point A. Okay, this is a free body. Okay, but the free body diagram, I need to complete, label all the forces and load. What do you have? You have a load P here, right? What else? You have a reaction, so I'm going to have a Ry. I know I don't have Rx because there's nothing applying in the x direction. Okay, that's it. You're going to reaction that the first bar pull in, so you're going to have a N1. Then the second bar going to pull it, you can have N2. Is this complete? Yeah, that's it. There's no other reaction or load you can apply there. Right? Okay, so this is a free, complete free body diagram. Okay, now can we write the equation of equilibrium? How many you can write? 2. Sigma Fy equals 0. Right? Let me just make this a little bit bigger. Okay, so we have the first, this is the free body diagram. So that's the first letter F stands for, right? Now, second, equation of equilibrium. We're going to have sigma Fy equals 0. And then we're going to have sigma m to a point. Let's say A equals 0. Okay, before I write it out, can anyone guess this is determinate or indeterminate? Indeterminate. Okay, now let's check with the equations. Sigma Fy equals 0. So you have Ry plus Ny plus N2 minus P equals 0. Wow, we have 3 unknowns. So now we find out we have 3 unknowns. All right. Now, the second equation we can write will be N1 times, they give you a distance, B, right? B. Then plus N2, 2B. Then minus P, 3B, right? Equal 0. Okay, write down equal 0. I found a lot of time people give me a solution, just write this thing out without saying equal to what. All right, so make sure you write equal 0. That's a complete equation. All right, now we have 2 equations, 3 unknowns. So definitely we cannot solve it based on these 2 equations. Therefore, it's indeterminate. Right? So we answered the first question. It's an indeterminate problem. Now, second question, how do you solve it? So we needed the Fed outcome. Okay, the F part, we already draw it there, free body diagram. Okay, second, equation of equilibrium, we already put it down there. So the next one, we need to find out the deformations, right? In this case, it's the elongation. That's the deformation, right? Okay, who elongate? The bar CD and the EF, right? So we're going to have delta from the CD, bar CD, or you can call it delta 1, right? Okay, what's the elongation? Should be N1, L. In this case, what's the L? They give you L1, L2, right? So we'll just say it's L1. We make it both equal, make it just easier. All right? So then you have this E1, A1. Okay, what about delta EF? Or delta 2? It will be N2, same length, L1, E, A. Right? So we have the deformation equation. Now, what's next? Compatibility. Okay, what's the compatibility for this equation, for this problem? Okay, what is compatibility? Remember here, what is compatibility? The relation between all the deformations, right? So if I move 1 step forward, the people in front of me should also move 1 step forward. How compatible we are, right? The movement between us, we are compatible. That's the compatibility. If I go 1 step forward, somebody step this way 1 forward, then we'll just clash each other, right? So that's not going to be compatible. Okay, so basically the relation between the deformations. So here the deformation is delta 1, the delta CD, delta 2, that's delta EF. So basically we need to find out the relation between these 2 delta. Okay, what's their relation? Now, look at this original problem, right? How would this thing move if you apply a load? It's like this is the beam, right? If I push here, see how this thing, look at this part and this part. Okay, I'm pushing here, right? Let's say this part is rigid. Now, if I push here, you see what? Everyone have to move, right? If I move down, every point must move, remain straight line. So this is a rigid beam, right? So therefore, if I make a cartoon of it here, okay, initially this beam is here, right? So you have this point, that's point A. This is a point, what do they call it? Point B. Okay, point B here. This is the, okay, now you have point C and point E. Now, if I pull it, imagine this is all rubber band. I can make it, you can visually see it. Okay, if I pull it, is this point going to move down here, right? Now, then this must remain a straight line. So let's see if I can draw it straight. Right? So you have to remain as this new one. So maybe I should use a different color. Let's see, I can actually select and change the color. Oh, didn't change. Okay, hold on. No, it doesn't work, this one. So I'll just redraw it. Okay. Oh. Sorry. Okay, so I changed the pen to a red one. So the new position would be like this, here, right? So if point B moved here, then point A should remain here. And this point D, this is E, so D should move to here, and E should move to here, right? They should move proportionally, because this beam will remain as a rigid straight line, right? That's how they are compatible to each other. Now, mathematically, what's the relation between this distance, right? This will be the delta 2. This will be the distance delta 1. Right? This will be actually the delta, let's call it delta B. So if I pull in the B point, move down distance delta B, then the point E and F, they will move proportionally. Otherwise, it's not a straight line anymore. You're breaking the spin, right? Okay, now proportional. Okay, how you write it mathematically? Because basically, they all corresponding to this angle. Okay, I can write this way. There are multiple ways. First, I can say tangent alpha. This is the angle alpha here. I can say tangent alpha should equal to delta 1 over 1b. That's AD, right? Or also equal to delta 2 over the 2b. That's the AE distance. Okay, or should equal to the delta B, then over 3b. Is that correct? So I'm looking at the 3 different triangles, right? They're all corresponding to this angle, alpha. So I call it tangent alpha equal to that. Right? Yes?
Again, just to clarify, all the links between A and D, E and D are the same.
Yeah, it's shown in the picture, original picture. So they gave you all our B value. Okay, yeah. Delta EF is N2. N2 corresponding to delta 2. Actually, this one should be delta EF. This actually is delta CD. I didn't get your question. What? Their lengths, yeah. L is the same. See, they're all lengths L1. I'll just make it easier. You can be different. Actually, you can put L1, L2. Doesn't matter there for solving the problem. They affect the final value. But for the process, it doesn't matter. Yeah, right? Okay, so basically, based on the triangles, the tangent, we get this relation. Okay, so this is the compatibility equation. All right. Any question about this compatibility? This is actually the most challenging equation in most of the problems. It's the relation of the deformations, right? How they compatible to each other, right? Because sometimes we say delta 2 equals, sometimes I see people just say, okay, so delta 2 equals 2 delta 1. Then I ask why. This is why. The equation of it is why. Because they have to be proportional. Yes?
Can we use theta?
Yes. Okay. Can we use sine? I say sine alpha. What's sine alpha? Equal to that, the same. Why is the same? Sine alpha not equal to tan alpha. Why they are the same? Because we talk about tiny deformation, small alpha. Actually, alpha equals sine alpha equals tan alpha for small alpha. So it doesn't matter, right? Or you can just drop this part. The easy one, you can also drop this part. Just say the three are proportional, right? Then you get the equation. Okay. All right. Any other questions? Okay. Homework today. First thing, finish this. See if you can solve it. Find out the relation between how much you move there, right? The load P, how the load P distribute. All right. We're going to go over more examples next time. Okay.
Is your